So continuing talking about sampling distributions for proportions. So we want to take advantage of the normal approximation. Anytime we can use information about, anytime we have a situation where we essentially have a normal distribution, we want to take advantage of it because we know a lot of information about normal distributions. Right? So the first thing we need for a normal, if we know that our sampling distribution is normal, the first thing we need is what are the mean and what are the standard deviation. So switch over. There you go. So the first thing we want to know is what's the mean and what's the standard deviation. Now, just as an emphasis of what we're talking about here, we're talking about the mean for sample proportions. So we often use a subscript p hat for both the mean and the standard deviation. Now, the mean of the sampling distribution for the sample proportions is just the population proportion, which is, in this case, we're using the notation p star. And the standard error for this statistic, this p hat statistic, the standard error is the standard deviation of the sampling distribution. And again, it's less spread out than the actual population. In this case, it's p star times 1 minus p star divided by the sample size. And then we take the square root of this. Now this formula, and I'll warn you now, this formula looks a lot like a formula you've seen before. This formula kind of looks like something like n times p times 1 minus p, and we took the square root of that. I'll come back and revisit this in a moment, but this has to do with the counts. This deals with counts, not with what we're talking about here, which is sample proportions. All right, so we're talking, this is the difference between how many actual successes did you observe, 1, 2, 3, 4, 5, counting, versus what proportion of your sample was a success. So that's the difference of what we're actually talking about here. Okay, so with these pieces of information, if the sampling distribution of the p hat is nearly normal, then we kind of have everything we need to do our calculations. So if we have that we have a normal distribution, then we pretty much have all that we need. Okay, so again, if our p hats are normally distributed, then we'll take advantage of that, the fact that we know a lot about. So if the sampling distribution of p hat is nearly normal, then we really have everything we need. All right, so what am I actually saying here? So let's say if we actually wrote this out, the idea is when we get a sample, we get one single sample. Okay, that's usually the world we live in. Okay, but I want us to imagine for a second that what we could do is we could get sample after sample after sample after sample. So we just kind of keep doing this again and again. In fact, if you wanted to, you could even think about getting infinitely many samples. Okay, if I'm looking at all of these possibilities, all of these p hat, well, if all of these are normally distributed, then we're looking at, well, we would actually have a normal distribution. We would actually have something that looks like this. We'd have a normal distribution. Okay. And where's the center of this normal distribution? Well, it would be at, the center of the distribution would be at p star. Okay, so this is at p star, which is really just mu of the sampling distribution, mu of p hat, that's just p star. And we know what the standard deviation would be. So the standard deviation for the distribution would just be sigma p hat. So again, remember, this is really just mu sub p hat, and that's the standard deviation. But if we have a normal distribution, there's a lot that we can take advantage of. All right, so let's actually work through an example with this. Okay, so we're going to work through an example. And the first step in the example is to confirm the shape. So this is the same example, but the first process is to describe the shape. Or to confirm the shape, sorry. So here's the problem we're going to do. All right, so this is the problem we're doing. Let me spread this out a little bit. Okay, so describe the expected sampling distribution. Let me raise this up a little bit here so I can keep that out of the way. Describe the expected sampling distribution for proportions of samples, in other words, that's the p hat, of size n equals 600 from a population with a population proportion p star of 60%. Okay, so let's actually kind of put a context around this. You know, it's always helps to think about a scenario. So let's think of this context. So here's really what we're saying. 60% of people in the town that we're focusing on, 60% of the people are going to vote for candidate A. Okay, so if we ask them, so we go up to someone and say, are you going to vote for candidate A, yes or no? 60% of them are going to say yes, they are going to vote for candidate A. Now, there might be more than one candidate, but we're just focusing on candidate A versus all the others, because it looks like candidate's probably going to be the winner. Okay, so the idea is if I poll 600 people, I'd like to know something about what that distribution would look like. All right, so let's start. So the first thing we want to start with is we need to confirm. So if we're going to describe the shape, we need to confirm that it's a normal distribution, or we need to say that it's not normal. All right, so we take n times p star times 1 minus p star. In this case, we have 600 times 0.6. 1 minus 0.6 would be 0.4. So multiplying this out, we get 0.6 times 0.4 is 0.24. 0.24 times 600. 144, move the decimal place. So this would be 144, which very clearly is greater than or equal to 10. So our variance is larger, so we have a normal distribution. So the implication here is that the distribution, is nearly normal. All right, so that's our takeaway message. So we can take advantage of that. Okay, so that's the first step in describing the expected sampling distribution. The first thing is to confirm and then describe the shape. All right, so check, we've done that. All right, so confirmed our shape. So now let's see. Now what we're going to do is we're going to come back here. Now this next step is then, okay, once we have our shape, now we want to describe the parameters in particular for that shape distribution, but you'd want to describe it for any distribution. These are parameters you probably want to describe for any distribution. So again, we're still focusing on this scenario, or this one if you prefer. All right. So let's actually go ahead and work this out. I'm going to move this one. Okay, I'm just going to move this out of the way a bit. Okay, so just another version of the scenario we're talking about here. All right, so let me erase some of this stuff. So I'm going to erase this part here. Okay. All right, so now the first thing we're going to describe is the mean and the standard deviation. Okay, so if we've got a normal distribution, we want to describe the mean, and we want to describe the standard deviation. Now remember, what is it the mean of? Well, it's the mean of all possible sample proportions. It's the standard deviation of all possible sample proportions. All right, so for this part, this is just P star. Well, we know P star is 60%, so we know the average of our normal distribution is at 60%. And then to calculate the standard error, we need the formula P star times 1 minus P star divided by the sample size. So I need to plug in this formula. So this would be 0.6 times 1 minus 0.6, 0.4, over 600. Okay, I'll let you do a little bit of the arithmetic here, but this would turn out to be 0.6 times 0.4 is 0.24 over 600. Taking the square root of that actually turns out to be a nice number. This actually turns out to be 0.02. So it doesn't usually work out, but these end up being perfect squares, so we get the value 0.02. Okay. All right, so what do we do next? Well, once we've we've described the distribution, it's nearly normal, given the mean and standard deviation of that distribution. So it's probably a good idea to sort of take a look at the sketch. What would the sketch of the distribution look like? All right, so now we've sort of described it, so let's talk about the shape. Or let's actually draw the shape. Okay, so again, taking this information here, I'm going to go ahead and rewrite this a little bit. So let me get rid of this part. So 0.02 is just 2%, so I'm going to go ahead and write it that way. All right, so for our population, the mean is at 60%. Our standard deviation is 2%. So if I were looking at this as a sketch of the distribution now, it would look something like this. We'd have our normal distribution. Okay, the mean here is at 60%. One standard deviation would take us to 62%. One standard deviation below would take us to 58%. If we kind of mark out a standard deviation each time along the way, 64, 66, so that's 3 standard deviations above. Going 3 standard deviations below would take us to 56, and then to 54, etc. Okay. So this is a sketch then of our distribution. So now with a sketch like this, we can ask questions like, well, what would be the range of usual values then? So what would the range of usual values be? Well, we could ask, if we're talking about this voting situation, if we really did poll 600 people, what would we expect as a usual response for the people saying, yes, we're going to vote for candidate A? Right? Well, in this context, there's a couple definitions of it really comes down to what is usual. And again, I'm guessing I'm going to predict one of the questions that's going to come up, but when we're asking a question like what is usual, if it's not specified in a problem that you're working on, you actually get to make the call for what is usual. So the question that we could ask next is, so given the scenario, what is the range of usual sample proportions? Now, what is usual? A couple definitions we've seen are within plus or minus 2 standard deviations of the mean. We've also seen different percentages of the middlemost values, the middle 90%, the middle 95, the middle 98. All of those are different and reasonable definitions of the usual value for the mean. All right, so let me go ahead and bring up my bell curve drawer. All right, so let's say we want the middle, let's say we want the middlemost to be the middle 95%. We want the middlemost 95% of values. I'm going to go ahead and plot this. So here is the plot that we want to actually analyze. So we want to know what is the range of proportions. So if this is the middlemost 95%, then there's 2.5% on each of these boundary values. All right, and here we have the percentages. 60% is in the middle. Going every one standard deviation would be 2 percentage points above or below. So if we go 2 standard deviation above, that takes us to 64. 2 standard deviations below is 56, and we see that those are close. But again, remember, the empirical rule, the count by thirds or the traditional rule, just gives us approximations. So if I really want the middlemost, if I want the real middlemost 95%, that's not actually technically plus or minus 2 standard deviations, but it's really close. So let's figure out what these boundary values actually would be. Okay. All right, so I'm going to kind of have to clean my screen up here a bit, or it's going to get too cluttered. So let's actually do the calculation for this. I'm just going to go ahead and get rid of, let me do this. Well, I can't move this, so I'm just going to go ahead and delete a bunch of what's on here. So I'll get rid of the sketch, start there. Okay, we already have this information, so I'll kind of put this, we can kind of get rid of this for now too. And I'll just move this over here. So we're asking, what is the range of usual sample proportions? I can spread that a little bit too. All right. All right, so to calculate this, probably the most straightforward way is just to use Excel. So we would enter equals NORMINV. We're looking for the lower 2.5%, and then we would enter the mean, which is 60%, and our standard deviation, which is 2. Now what gets tricky here is because we're talking about percentages for our means and standard deviations, but we're also talking about a percentage for the percentile, and this is where it does get a little tricky with these problems. And this comes out to be 56.08%. I would then do the same calculation, but for the upper 2.5%. So in that case, we would actually be looking at equals NORMINV 97.5%, comma 60%, comma 2%. And that would give us the value 63.92. And if I'm trying to pick the innermost range of values here, let's say rounded to 1 decimal place, 56.1% is in the interval, 63.9% is in the interval, so that's probably a good choice. So the range of values would be somewhere in 56.1% to 63.9% would be the range of expected values. So the range of usual sample proportions would be somewhere between 56.1 and 63.9. So in this case, we're using the definition of usual equals middlemost 95%. Yeah. Well, I said it, but I didn't actually type it. So that is key here. Okay, I'll kind of move these things around a little bit just to sort of. All right. Again, just going back to the picture just so we can see it again. So then these values just in context. So when we're looking at this curve, this is what we just said was 56.1%, and it kind of makes sense, just a little above 56%, and this is 63.9%, just a little bit below 64%. Okay, so that would be the range. Now, that doesn't mean we couldn't randomly select a sample that would have more than 64%, but it's only going to happen about 2.5% of the time. And the higher we have this boundary, the less likely it's actually going to happen. All right, now what I'm assuming, if you're like me, most people are not going to want to do this. Most people are not going to want to do this out by hand every single time they have to do one of these calculations. All right, so let me go ahead and back to the whiteboard. All right, so here's what I'd actually recommend you do. So I'm going to go ahead and save this. And what I'm going to do is I want to show you how you do this calculation doing Excel. And I call this version number 1. Okay, so I'm actually going to